All right, thanks for coming, guys. I'm going to talk about our new, relatively new prosthetic foot offering called the Skride, Seattle Skride, prosthetic ankle foot system. My name is Jay Humphreys. I'm a double amputee myself, as you probably noticed. Lost my legs in 1991, first Gulf War, and got my degree after I was out of the Army in mechanical engineering. Shortly after I finished my degree, I was picked up by a U.S. manufacturing company in Pasadena. I was there for only a year. The company was absorbed by Seattle Systems, and so I moved up to Washington State, where the manufacturing was done and for Seattle Systems. And then in the late 2000s, Trulife purchased us. Been with Trulife ever since. So was located in Paulsboro, Washington, and now all our manufacturing for prosthetic feet is done in Bellingham, Washington. So it's about an hour north of Seattle. We have a couple other facilities throughout the world. So Trulife is actually based in Dublin, Ireland. We have a facility in Sheffield, England, and a facility in Canada, and a facility in Jackson, Michigan. So just kind of going through the basics and kind of the overall briefing of the Skride is the goal of this course. So SSF 400, Seattle Skride foot. It's a dynamic response composite shank prosthetic foot with approximately mounted shock absorber with torsion. So as y'all are certainly aware, there's quite a few offerings of this general layout of type of foot. And throughout the presentation, I'll kind of explain what I think makes ours just a little bit different and why ours could shine and perhaps be a good choice for your patients. So intended use indications, obviously lower limb amputees. You need at least 7 inches clearance. And the way we always calculate the actual clearance is we kind of measure to the midpoint of the sphere. Because that's where the or the mating adapter would sit. So you have from the floor, including the foot shell, to that line is about 7 inches. It's geared more towards the medium to higher activity level patients, and with a maximum patient weight 150 kilograms, 330 pounds. Foot size available 22 through 30. So of course, if you don't have room, you don't have room. So less than 7 inches build height, you're going to have problems. Because it is geared more towards higher activity patients. Low activity or people in a kind of a weakened state probably won't do too well with this foot. If your patient exceeds 150 kilograms, it's just not rated that high. When you get down below 60 kilograms, probably it wouldn't be a good choice either because of just the category offerings we have. The lightest patient we had was about 100 pounds, and it was just, he wasn't heavy enough to drive it. So, and of course, less than 22 centimeters that's the smallest we make. The product line comes in 3 stiffness categories, and so we call it number 1 being the softest, 3 being the stiffest. Foot sizes 22 through 30. The cosmetic shell is split toe cosmesis. People that like it a lot, and then other people could take it or leave it, but it is a good feature. It comes in 2 different colors, light or dark. And what's not shown in the photo here, but it also comes with the Spectra sock. It's pre-assembled with the Spectra sock. So that's our selection chart. The way we tested the feet is that we used what we rationalized as medium to high activity level in terms of the loads that were applied when we did our testing, our fatigue testing. And so we kind of based our initial categories on somewhat high activity level patients that were, so the category 3 would be for somebody that's 300 pounds, pretty active, 100 kilograms, very active, 80 kilograms, very active. And then, so you get into the realm of, you know, it's sort of subjective what these terms are, I know. And a lot of this is due to extreme impacts or what a person might be doing in their everyday life, and whether they're carrying heavy loads or just what their job description is. We always recommend if you think the patient's on the verge of, or sort of at the higher end of that range, to just go up a category. So, first part I'll talk about is the lower subassembly, the composite structure, and then I'll get into how the shock works. So the shock absorber itself allows up to 15 millimeters of vertical travel, over 28, we say 28 degrees of range, and that's 14 in each direction. That's with a specific load applied. It'll actually go further than that in severe overload conditions, and it will spring back. There is, internally, the way it's made, there is not a internal mechanism to stop it. So the bulb itself is the torsion spring. So you could twist it quite a bit if you like I said, in a severe, like sort of emergency situation where somebody gets their foot caught and they fall down, it'll twist quite a bit. But as soon as you unload it, it'll kind of unravel, or not unravel, but it'll spring back to its original position. So I'll talk about the composite structure. So in around 2017, we had a product that fit just the L5981 L code, basic blade type foot, but without the shock absorber. So if you imagine this foot, but just with a pyramid attached to the proximal end. We learned a lot from the development of the composite substructure. You know, based on what we learned and our experience with that, we just use that as the building block for adapting it to include the shock absorber. The composite components are fabricated in two separate pieces, and then they're attached, bonded, and joined together, all made of aerospace grade carbon fiber, pre-preg. We cure the parts in an autoclave, and then we cut the parts out according to the size needed with our water jet machine, and then we join them together at final assembly. The way we join the two parts, so instead of using metallic fasteners, we wanted to keep the structure as light as possible. So the keel portion and the shank, we call this the shank portion, are bonded together with a very high grade epoxy, but just epoxy alone wouldn't survive, especially in sort of a peel condition. So if somebody had like the old flat tire, somebody steps on the back of your foot, epoxy wouldn't survive that. So what we introduced, instead of using metallic fasteners, like I said, we basically use the same carbon fiber to create, in a sense, rivets that are cured and hold the two parts together. One of the things that in the research that I did to kind of justify us even trying that and attempting that was the fact that from this article I cited, there's that method of joining parts has been used in the aerospace industry, is really successfully used in F-18 Hornet. So they were able to eliminate a lot of fasteners in that airplane by joining parts with basically composite rivets. So it lightened everything, and one of the side benefits that had even better fatigue life than a metallic fastener in a lot of cases. Just to illustrate, and this is just from, I believe it's from the Loctite adhesive handbook, a bad joint and a good joint when you're just bonding two members together. And you can see, like, if you look at the top one or maybe the third one, we're like telling, it's like we're doing what they say not to do, right? But because we use those composite, what we call Z pins, and we call it Z pins because if you think, X and Y, and then that'd be Z. The Z pins allow for, a bonded joint to be successful, without because a good joint would have been extremely complicated and just wouldn't be conducive to speedy or efficient manufacturing for what we wanted to do. So the heel response, and this is similar to other products out on the market. So you have the shank and the heel spur, and to actually control the behavior, or the performance, or the response of the heel at heel strike, we have the polyurethane wedge here. The Skride, we redesigned that part. It's very similar to what was initially used in the Zenith, the precursor to this product. But we learned some things, and one of the things we learned and was a complaint was noise, squeaking. Typically, if you have a smooth polyurethane surface touching another smooth surface, it just sounds horrible after a while. It just sounds like a squeegee. And so one of the things we did, just to pretty simple solution, was to hopefully you can see that the way we just cut the profile, it's got like a corrugated surface, so you don't have a smooth surface to create that pocket of stick slip which would cause noise. Another thing that we did is we really liked the appearance of the red color. Everybody liked the red color. So instead of having different materials for different categories, we just had the one material, but we changed the stiffness and response just based on the overall profile, how it was cut. So a number 1 and 2 category foot gets the same shape, and then a category 3 foot gets a much larger one to act as it is a stiffer spring in a sense. Also, we include the 3 bumpers, which I mentioned earlier, 3 heel inserts for the bumper, and these are optional. So if you need to stiffen up the heel response, these are in 3 different diameters, and you could just slide it into the hole there, and it'll increase the stiffness and make the heel response change. But like I said, it's optional. You don't have to use that. Just overall, benefits of the composite substructure. It's lightweight. It has a smooth transition from heel strike through rollover. Even though it isn't a split, it does, because of just the way it's designed and the way it's connected just up here, essentially. There is some ML articulation. Not enough to claim multi-axis L code, but it is enough to, it is noticeable. The patient will feel it. The forefoot has really good response in terms of the dynamic energy release. I like to explain how it feels to me when I'm using a foot, and even rolling this back to the precursor, the Zenith foot, before it had the shock. I liken it to having almost like a pole vaulting kind of sensation if I need it. So if I'm walking up a hill, for me it's more efficient for me to actually, as I walk up a hill, I'll actually load the toe, I kind of pulse it, and the forefoot will kind of coil up, and it'll help propel me up the hill. But it's not so much that it's you don't feel wobbly. It's not so flexible that that you're hunting for your balance. So it's smooth enough, but there's that energy, I guess, reserve, if you will. If you had to accelerate to get out of the way of a car or something, you can kind of run pretty quick. As you can imagine, the these are prevalent on the market for a reason. People like it, and not just for the reimbursement, but really what it does for the user. So it really helps to soften the harshness of impact, jarring, if you will. Reduces the overall stress on my lower back. Makes things just a lot comfortable. Makes wearing the prosthesis a lot more comfortable throughout the day. So at in conjunction, the axial rotation, having that axial rotation just really takes the bite out of the proximal brim of the socket. If I go from wearing this foot to a foot that doesn't have the axial rotation, I really miss it. And I would say, for me personally, I really like it, especially on my transfemoral side, just because of how things fit up in the crotch area. It just takes a lot off your body, but it's good for the BK side as well. I mean, it just takes some strain and stress off of your knee. So I'm going to talk a little bit about just basics, how things were kind of evaluated, in terms of the vertical load response of the shock itself and the torsional response. So back in 2010, there was a group of representatives from a number of manufacturers that were invited to participate with AOPA to sort of quantify what the different L codes really meant. So the idea was at the time, to kind of put the brakes on some of the companies that were claiming L codes that they really shouldn't have been getting. But things like, how much should the shock compress for you to even justify or claim an L59 87 foot? How much should the foot twist under a torsional load? And then how should that even be measured? So in terms of the torsional aspect, what was decided and agreed upon at the time was to take the foot, apply an 800 Newton vertical load. That's about what I weigh. 800 Newtons is about 75, 80 kilograms, right? So if I was just to stand here on one foot and then apply a 20 Newton meter torsion to it, how far will it go? If we were to run our foot under those conditions, we would get 14 degrees in each direction, okay? And that 20 Newton meters it's significant when you're talking about if you were to apply that directly to the end to your knee, So it really does help take the stress off your knee. It'll go a lot further than that. So if you see here on the right, this is an example of what we do to that shock assembly after we assemble it. It's part of our quality check. So we apply almost a 50 Newton meter torsion to it, and it'll twist about 45 degrees with that amount of torque. But I could tell you, you would not want somebody to take your knee and try to twist it with 50 Newton meters. It's quite a bit. So, but it will give that far. At the end of the presentation, I could share with you some more things that have happened to me over the years that are even worse than that, and the foot just sprung back to its original shape, which is a good benefit. As I mentioned before, the vertical shock, especially the vertical component of the shock absorber, is really helpful for just everyday life when stepping off of a curb, getting out of the truck. Anytime you're just stepping off something high, and also, of course, for more active events, sports or activities. And I'll show you in a minute how the actual measured response from of that shock in the vertical loading condition. And of course, the twist, turning. And one of the things I didn't mention a second ago is also just walking around in a tightly confined area and turning. Just doing this in a day-to-day condition. If you're in a closet, you decide to turn, or you're waiting in line at a crowded store or something. You have to twist, turn. It just takes a lot of load off the rest of your body. What we like and what we think is one of our key benefits of our design, of our shock, is that the internal spring can be preloaded. So when it's shipped, it's at the loosest condition, and you as a practitioner, if the patient doesn't like it to feel that soft, you can tighten that screw on the top of the pyramid, and significantly make the vertical shock feel stiffer. So some people like to feel like they're walking on a marshmallow, but other people are more active, or if they're from their day-to-day activities, they're lifting and carrying heavy things. If the shock is allowed to compress too much, you feel like you have to like get up out of that hole every time you take a step if you're carrying something heavy. Personally, I like to tighten mine a little bit, I'd say about 2 turns from fully backed out. I could make mine stiffer, but 2 turns seems about right for me. But the spring is not replaceable by the practitioner. So the way it's designed right now, you can't take it apart. But there is an overlap between a category 1 and a category, up through the categories, there's like a definite overlap if you tighten that screw. And this is basic, theory of Hooke's law and how a perfect coil spring works mathematically, right? So it's F equals Kx. K is your spring constant. Then in addition to that, it's the preload. So in this example, there is no preload. So you just have and I use a simple example here. So the spring rate or the spring constant is 10 kilograms per millimeter. So from 0 up to, say, if I was to pick 10 millimeters of displacement, it would take 100 kilograms of force to make it go that far. One thing about if you don't have any preload, that means the moment you start touching it with any bit of load, it's starting to compress, right? Which, for a prosthetic foot application, you don't want it to sink with almost no load. You want it to kind of hold the person up until they actually apply a bigger load to it. So in that case, so you don't want it to sink because you'll feel like you're always stepping into a hole all the time. And just an example of, for an external spring, shock absorber from either a mountain bike or a motorcycle. Usually there's a collar of some sort that you can twist to tighten and increase the preload. When that collar is first touching it, it's 0, and then there's an amount of preload that it'll allow you to adjust. But with this kind of mechanism and with our mechanism, turning that screw does not make the shock get longer or shorter because the mechanism itself is trapped. All you're doing is compressing the spring, right? So in that case, if you're using a simple example again, if I was to preload that spring 5 millimeters, I could push on it with 50 kilograms and it's not going to budge, right? But as soon as I exceed 50 kilograms, then it'll start to move. So in this case, I'm not changing the spring rate, I'm just shifting it. So with our design, it's essentially like that shock absorber on the mountain bike, but flipped so the mechanism is internal instead of external. And instead of a coil spring, so the coil spring gives you that perfect linear load curve. Because we use a polyurethane spring element, it doesn't quite behave like a mechanical or steel coil spring. It has a little bit of a different curve to it. What we use internally in our unit here is material called Volcolon. It's when it comes to polyurethanes, there's several different flavors, if you will. And the polyurethane that we use is the Volcolon is trademarked by Bayer, and there's only a couple companies throughout the world that'll make it, and it actually goes through a vulcanization process to get it to the properties that's desirable for especially for this application. And one of them being the rebound effects and the resilience. A lot of polyurethanes, lesser polyurethanes are prone to a compression set, but we chose this material because it's highly resistant to the compression set over time. So it's not gonna change a lot over time compared to more of like a consumer grade polyurethane would. So here I have the three different categories of, so this was measuring just the shock alone with the three different spring elements. Category 1, unfortunately, the scale is different than the other two, but you can see that essentially by tightening the preload screw, you're making it stiffer. So the difference, so this is zero preload and 4 turns preload. So the difference being at 150 kilograms load, so you got your heaviest patient rating for that number 3 foot. So with 0 preload, that person standing with the other foot up in the air, the shock would compress a little over 7 millimeters. And if you tightened it 4 turns, the shock would only compress 3 millimeters. You can see the difference there. And you can see how the three kind of have an overlap to it. And one of the reasons, like I was kind of saying before, the polyurethane does act a little bit different than a perfect steel coil spring. It kind of ramps up as you get further into the stroke. But that's another benefit of this design is if you land on it with a pretty severe shock load, it just gets stiffer and stiffer and stiffer, but you never feel a metal against metal impact at the end of its stroke. So it just has that internal effects of, it's not actual like damping in a sense that there aren't any valves or anything inside the shock, but just the effect of trying to squeeze that polyurethane spring inside. And as you're squeezing it vertically, it's sort of expanding horizontally. So it's kind of putting drag on the walls of the inner tube. So it just gets tighter and tighter and tighter as you compress it higher. So like I said, one of the things you would not want is to have that metal against metal hit, bottoming out. That's a harsh feeling. It's not comfortable, but this doesn't have that. Now just kind of talking about some of the just basics. Bench alignment, we just recommend starting point, straight down the middle of the pyramid, down the midline. If the heel feels too stiff, you could shift the foot anterior. It'll effectively make the heel feel a little bit softer. Of course, the trade-off is then you get a longer toe lever. Might or might not be a bad thing. Same thing if it feels too soft, you can shift it backwards, but then you're kind of falling off the toe, shorter toe lever. You can insert one of these if you want, if necessary. You have the 3 different options, or you have 4 options really. You have nothing and then 3 different diameters. If once you decide which one works best, all it takes is, we recommend don't bond it in when you're trying it out, but once you've decided which one you're going to use, just tack it in there with like a CA, like Loctite 401. We found that Loctite 401 works really well with the polyurethane. Also, surprisingly, a really good one is the Gorilla Glue brand of Loctite, or I'm sorry, of instant adhesive. It's up there with Loctite's best offerings, and it's pretty good for just supermarket or a big box store kind of selection. Similar to what I showed earlier with the vertical shock, and this is kind of just describing or showing what the heel response is. The solid line on these two, or on these graphs, is with nothing in the inserted in the hole, and then just showing how it does stiffen up the response if you put. I didn't do all three, but just to show you that there is a response or a change in response. The fact that this isn't the same sort of mechanism, there's no preload because you're just basically saying, okay, what happens when this foot is in the air and you land? So you're going from 0 to all of a sudden that's the response. Just kind of showing the test method. So there's the angle, the plate is tilted at negative 15 degrees. And that's based on the peak loading conditions of the ISO foot tests for the cyclic fatigue tests. So negative 15 is when the peak load occurs on heel strike. Conversely, toe off happens at plus 20 degrees, but we're just doing the minus 15 degrees here. So I'm just going to talk a little bit about our design and development process. What we go through to come up with a foot like this, and how do we get it to the point where we think it's safe and worthy of people using it. There's always the initial concept. We could come up with all sorts of crazy ideas at first, and everything looks great on CAD, in SolidWorks. You can make something look really beautiful and awesome in CAD, but until you start actually testing it, then you find out what's wrong or what's wrong with your ideas. In our case, we knew we wanted to use the Zenith lower composite structure as the building block. Utilizing the Zenith as that initial building block, we knew, okay, well, we're going to have to bolt that shock absorber to that composite structure and then test it. Because if the bolts fail, all is lost. It's like a oh crap moment if the bolts fail, and that cannot happen, right? So the first thing we did is just on the image on the left, we pretty crude, simple design, and it would be like the worst case scenario for you imagine this shock that was completely locked out, just solid. Test that 3 million cycles, make sure those bolts hold tight and don't fail on you. So we had a couple iterations of getting the right size bolts, the right configuration of how it fit. And then we went to a pretty crude version of the shock unit, which was kind of based loosely on that first kind of test block. So the one in the middle is just a really simple, crude shock absorber, just to basically test the function and see what it felt like. It's still making sure that the bulb was going to survive. These tests, so we would do these tests 3 million cycles until we were happy with that, and then we'd kind of go on to the next iteration. So the one on the right is like the first machined part that kind of looked like the concept we had designed in SolidWorks. And as we were testing that, it looked great on the design. The parts looked great, and everything looked beautiful. It's all nice, shiny. It works. And you could compress it and it makes some moves and everything. And you test, just do some functional tests. And I walked around on it a little bit. It's like, yeah, it feels pretty good. I'm not gonna take it home though. Not until I know that thing's not gonna break underneath me. So the requirement for the ISO 22675, and that's the foot testing. ISO requires 2 million cycles for foot ankle systems. For our higher end units, we know that it's kind of assumed nowadays that there's at least a 3-year warranty. So that we test to 3 million cycles for our high end feet like this. This one. These are just screen grabs from a video, so I'll kind of cycle back and forth. I didn't include a video clip in here because I didn't know how it was going to work with our system. But just showing how if you're not familiar with the ISO test standard, it does a pretty good job of simulating actual the loads that occur during gait, during normal ambulation. And it's a load control test. So you have a defined load profile. And so as the test proceeds, it's not just going through like a simple sine wave. It's load controlled. So I mean, it's trying to hit that target load, because to simulate a person walking, the person weighs the same. It's not that the deflection of the part is going to happen the same every time. So if something starts to fail, it's going to push further and further and further and further, right? And the way the system works, we set our limits in the software. So if it deflects further than, say, 10 millimeters than what it was when it started the test, then it'll stop and say, okay, it gives you a chance to take a look at what went wrong. And that was our first beautiful machine part, and we went for gold. We were looking to qualify this one at 300 pounds, high activity, and snap. And that happened only at 300,000 cycles, right? So that's the way it goes pretty much for everything we've ever designed. You know, we make our best guess initially, machine the part just based on our past experiences, what we think might work, and almost every time you'll see your beautiful design just get ripped apart like cheese. Stress analysis, finite element analysis software or routine that's built into SolidWorks is actually not that bad, but you have to know where the failure. It's kind of a chicken or egg thing. You have to know where things are going to fail before the FEA program even makes any sense, because it's garbage in, garbage out, right? So basically, we test something, see where it breaks, and then we try to simulate that on the computer. It's like, did that actually? Can we match that? And then make design enhancements based on something that we know is going to fail at a certain point. So, you know, this is basic engineering 101, statics diagram. So we were able to kind of estimate what the loads were, and then plug those loads into the FEA program. The image on the left is using those loads that were calculated. They're showing you where the hot spots are. It's like, okay, yeah, so our model and how we define the loads in the software actually kind of represents what actually happened to this thing, right? And then from there, we would take our model, you know, beef it up in those locations, or make either material choice change, or increase the thickness of the structure. In this case, in this region, where that part was, where we saw that crack occur, or where it initiated, and you know, we machine new parts and see what happens next, right? So in that case, so we machined a new version of this, the lower, what we call the lower tube, this part. We beef that up, and then it becomes a game of chase the stress. So now we fix that part. Now the next thing to break is, now that thing breaks, right? So kind of do that. So it's an iterative process, you know. It's one of my colleagues used to say it's like plugging the hole in the dam, you know, or in the dike. You know, you block the flow of water here, and it's like it springs out somewhere else, right? So so initially we were trying to make this as light and as simple as possible, and that the upper structure was going to be all aluminum. That didn't work out well at all. That failed pretty fast. And then we ended up kind of using what I've learned over the years from riding dirt bikes and things. So the upper cap is aluminum, but it's press fit into this part is actually chromoly steel, but it's salt bath nitrided. It's for the wear resistant, hard outer shell. We didn't need the chrome. We realized we didn't need the chrome coating, but the hard outer surface of that salt bath nitriding prevented any wear of the bushings. The bushings wouldn't wear into that surface. But then we started seeing, okay, stress concentration right where that crack initiated. That was because I had a little hole for a set screw to line up. And of course, right where you drill a hole, that's where it's going to break. Yes?
Would the red thing break always before the metal?
The red thing? The bulb?
Yeah.
No, so
Is that part of the test? Is that on?
So this is just after the test, we dissect it, because a lot of times, I mean, one of the things that would happen is the test would, it always happens at night when we're not there, you know, because the machines are running 24/7. But what would happen is, I can kind of back up here. So like, well, in that case, it was obvious it had nothing to do with the bulb on this one. But in the case of where this part broke, what we would see is come back in, the test is stopped, and it's just sitting there because it retracts, the machine retracts it when it's done or when it decides to stop. And it's like, well, what the hell's wrong with it? And then you grab it and it's like, it's fold in half, right? So the bulb would hang on. And so in a sense, I mean, if that, we don't want that to happen ever to people. That's bad, you know, but if it did, the bulb is still kind of holding on like you had a broken leg and it's just hanging on by sinew. So the bulb sort of held it together.
So it didn't break, because in my experience, when I look at that, I'm thinking old school. Okay, that'll break within a year. I'll have to
oh no,
replacement.
No, the bulb is gone well beyond 3 million cycles. So we yeah.
Right.
Yeah. So we've you know, it said we'll test to 3 million cycles for our official, like just to cover the fact that we warranty it for 3 years. But in some of the tests we did for just to prove it to ourselves, we don't want to go 3 years and then break. You know, we've run some of these samples out to 5 million. One part will break, we'll fix that. Then something else breaks, we'll fix that. So it's pretty time consuming. You know, it took at least 2 years of constant testing and development to get it to the point where we're ready to kind of get it out onto test patients. You know, just to kind of illustrate how long it takes, our test machines, we would run them at 1 1/4 cycles per second. And to achieve 3 million cycles, it takes about almost a month, about 28 days. And that's running 24/7. You know, you can imagine you get to 2,900,000, and then something breaks. Like, you know, we'd have some other variations or samples like lined up behind it, but so you know, you get to that point. It's like, you know, design change. Back to the beginning almost, you know, for qualifying it at 3 million cycles. Yeah, especially when we're getting into the higher load, the higher category, the category 3 foot. You know, that was a hard one hard nut to crack, so to speak. SSF 400 is the marketing code that comes with the light colored foot shell. 403 has the darker colored foot shell. As I mentioned, PDAC approved L codes, up to 15 millimeters travel, 14 each direction, axial, under the loads I described earlier. For a category 2 foot, size 27, it weighs 937 grams, and that's including the foot shell. Category 3 foot is rated up to 150 kilograms, 330 pounds. Warranties for 3 years for the mechanical structure, everything mechanical is warranted for 3 years. The foot shell is warranted for 6 months. In my opinion, these are like tires, you know, they wear out like shoes, you know. So 6 months, and they're easy to pop off with a shoehorn. And just a couple of examples. Is one of our test patients, not even a test patient, he's a practitioner himself. He's really enthusiastic about, you know, what he had to say after using this foot. You know, we had between 2000, March of 22 and March of 23, we had sent, not including me, but not including me, we had 14 units for evaluation out on people, and we didn't have any failures of any of them. And almost all of them have kept the foot. They don't want to give it back. So they all liked it. The only one that it didn't work for was the one I sort of mentioned earlier. He was a young kid, and he only weighed about 100 pounds. And just the way the shock was set up, it was just too stiff for him. And even the composite structure was a little bit too stiff for him as well. You know, and also just being that small of a kid, it was a little bit, just even the 937 grams felt heavy to him, you know, a little bit too much. Some of the other comments we've had from people is, you know, in addition to just the overall comfort they get, it's like this. Paul, kind of one of the things he mentioned is how, in addition to what the composite structure gives back in ambulation and the dynamics of the composite structure, that in conjunction with the shock absorber gives you just an extra that bit of push off. So he felt like he could just run around, sprint, and he really enjoyed it for being able to play soccer with his kids. You know, me personally, that's my game. So I ride dirt bikes up in the mountains, and I'm riding that bike up in extremely steep, technical, tight terrain in Washington. And I drop that bike all the time. And I'm always having to pick it up. And I have the bike land on top of me. And you know, one of the things that's happened to me before is I crashed and I kept on rolling, and my foot was trapped under the bike. I rolled, the foot twisted 180 degrees. And when I got the bike lifted off me, the foot just sprung back to shape. So it can handle pretty extreme, horrible incidents, and if that had happened with another foot, that would have really hurt my knee. You know, another thing, just having foot that I can rely on. What I always think about when I'm going out in the mountains is the common denominator is that bike could quit running at any time, and it has before. I've had to hike out 6 miles in the mountains. That sucked, but you know, I could do it. You know, with other feet, you know, probably wouldn't have been as great. You know, especially walking down rocky hills and things. You know, perhaps would consider, if you have patients that are candidates for trying a foot like this, that you might consider trying it. I think they'll be pleased. I think you know, we've had a lot of favorable response so far, and I think your patients might like it.